Hello Internet, my name is Quinn and this is Blondihacks. This is Mill Skills, a series of quick videos on getting started with your vertical mill. This is episode 4, Basic Milling. Let's dive in. Probably the most foundational thing that you need to know about milling is direction. There are two milling directions, conventional milling and climb milling. And I'm sure you've heard these terms, but it can be a little bit difficult to understand what they mean, so I'm going to illustrate it with this setup right here. So I have here a comically oversized milling cutter, and standing in for the stock is this material here, which you may not be familiar with. This is a carbohydrate foam product. The ore is typically found in forests, and the smelting process is very low temperature. It's actually room temperature. Pretty interesting. It's difficult to work with. For the life of me, I can't seem to find the right settings on the welder, and the dust from this will actually kill you very slowly, so be careful when working with this stuff. Okay, so imagine we're deep in this exaggerated cut here. The milling cutter is always going to be spinning this way, but the material is being pushed by the table, and it could be getting pushed this way or this way. If the material is moving this way, that's conventional milling. If the material is moving this way, that's climb milling. Remembering which is easy. Climb milling is the intuitive one and conventional milling is the other one. So if this material is moving this way and the cutter is spinning like this, you can see that the cutter is actually wanting to climb its way up the hill of this cut. That's exactly why it's called climb milling. But what's interesting is these two different operations have very different cutting properties. In conventional milling, you can see as I approach the curve of the previous cut, this tooth here, it starts out on a very gentle slope and progressively eases its way into the material. You can see how that would happen here. And so the tooth actually starts out rubbing, and then eventually, as it keeps getting pushed into this slope, it starts to become a cut. Now over here on the climb milling side, when this tooth impacts the material, you can see it's basically at a right angle to the material, and so it's going to dig right in and immediately start cutting. There's no easing into the material. It's biting right in and starting a chip immediately. So because of that better cutting action, climb milling actually produces better chips and also results in a better surface finish. Conventional milling, meanwhile, because the cutter starts out rubbing, the cut doesn't start very well, and so you get a worse surface finish and you also get more wear on the cutter. So given all that, climb milling sounds like the way to go, right? But all you ever hear is that climb milling bad, conventional milling good, right? That's what everybody says. And it's basically true, and for one main reason, and that's rigidity. Because of this climbing action that the cutter is doing in climb milling, the power of the mill is actually working against its own rigidity. It's using its own power to push the cutter off track. So there's a tremendous demand on rigidity when climb milling. Whereas conventional milling, because the cutter starts out with very low tool pressure, and then as it digs in, it tends to pull itself into the material. The rigidity demands of conventional milling are much, much lower. And if you get aggressive with climb milling cuts, you can actually feel that climbing or that pulling on the table. And you'll know that feeling if you've come from a DIY or a woodworking background and you've used a handheld router. You know that when you use it in one direction, it howls like a wounded banshee, and when you use it in the climb milling direction, it attempts to murder you. And that's how you know which is which. So on high performance mills like modern CNC machines, climb milling is actually preferable, and the books will actually tell you to prefer climb milling. But the conventional wisdom says climb milling is bad because, well, most of us have older manual machines that don't have as much rigidity, and for those machines, conventional milling is much better. But we can get the best of both worlds if we do most of our milling conventional, and then when you need a really good surface finish, you can do a light finishing pass climb milling to get the best possible finish. Yeesh, so much talking. Let's make some chips right after a little more talking. So I'm going to do a conventional milling pass and then a climb milling pass. And remember that the cutter is spinning this way, and milling cutters always spin the same direction. They spin clockwise when you're looking down on them. That's how I remember it. And so you'll see that if the material is moving this way, the cutter's spinning this way, that's going to be a conventional mill. And then if the cutter is spinning, of course, the same direction and the material moves this way, that's going to be a climb mill. Here's the kind of finish you can expect from conventional milling. It's smooth to the touch, but under the macro lens you can kind of see these vertical ribs that are caused by the start of that chip formation being a little funky. And here's the finish from climb milling, all the same settings on the machine, and you can see that the finish is much nicer. You can still see the tool marks just barely, but mostly what you now see is just the horizontal grain in the aluminum. So assuming you have an average, less than superhumanly rigid mill, the way I like to remember which is better is that conventional milling, the cutter is fighting the direction of the material feed, whereas in climb milling, it's following the direction of the material feed. So you want to be a fighter, not a follower. And I find that mnemonic useful because it's easy enough to visualize climb milling versus conventional in 2 dimensions on the bench, but here in the heat of battle set up on the mill, it can be a little harder to wrap your brain around which direction the material is moving relative to the teeth. So imagine the cutter always moving in slow motion like this, and you can see that if I move the material this way, you can see that that material is following the teeth. It's going with the teeth. So following, that's climb milling. If the material's moving this way, you can see that it's resisting the direction of the cutting teeth. It's fighting the cutter. So be a fighter, not a follower. We're going to talk about face milling first, which is generally the first operation that you're going to do on a given part, and it's also the most common operation that you're likely to do on the vertical mill. At its most basic level, face milling is how we make things flat, and that's kind of the superpower of the vertical mill, is it makes things flat. So you might take something like this here, which is a rough bandsaw cut. It's very typical of what you're going to start with because you're going to rough cut your stock to the very approximate dimensions of the part you're going to be making. And after face milling, you get a nice smooth machined surface like this guy. So face milling turns this into this. Face milling on the vertical mill is analogous to the facing cut that you start with on the lathe. It's the first operation that you're going to do. It gives you your first reference surface, and then typically how on the lathe you would then turn the outer diameter of the stock to some major diameter that's going to be the basis for adding your features to the part. On the mill, we're going to face this first surface, and then we're going to typically square up the stock by face milling all of the sides to get it to the rough outer dimension of our part, upon which we can then add features. So here's a selection of milling cutters that you can use for face milling. So over here we've got your basic end mills, and these come in a few different flavors, which we'll discuss here in a moment. And then in the center here we've got a couple of examples of shell mills, which are like great big end mills, except they have a hollow center in them, sometimes filled with jelly. And then over here we've got a fly cutter, and then also a great option are face mills. These are typically going to be set up for carbide inserts, and those are a great option for larger machines. For smaller home and hobbyist benchtop machines, I tend to prefer the high-speed steel options, so I like the shell mills, and for larger surfaces, the fly cutter. Let's take a closer look at the geometry of the humble end mill. It's the most common tool that you're going to be face milling with, but these guys are marvels of engineering, and they are called end mills, and they have cutting edges on the end. So you might think that they cut on the end of the end mill, but in fact that's actually not really how these guys work. So let's say I've got this guy set up in the mill, and I dial in some depth of cut, and then I start moving this guy across. You can see how it's not really the bottom of the mill that's doing any cutting. It's actually really this front edge of the bottom of the flute that's doing the cutting. This corner here and this edge. So depending on how deep your depth of cut is, if you're doing a 50 thou cut, then the bottom 50 thou of the side of this flute is what's doing the actual cutting. Let's talk about the most visually obvious difference between different end mills that you're going to find. First is the color. Sometimes they're silver, sometimes they're yellow, sometimes they're purple striped or whatever. And they have different numbers of flutes. So the most common you're probably going to encounter are 2 flute and 4 flute. So what's all the differences here? Well, the color is generally some sort of coating. Now in this case, this yellow color on these guys comes from the titanium nitride coating that they have, which is a very common kind of entry-level coating for high-speed steel mills, and basically it just increases the hardness of the mill. Now you'll also find other coatings to increase lubricity or increase wear resistance or lots of other valuable properties. And these coatings come in many flavors, and they're about 80% science and 20% marketing. But compare that to this silver colored mill here. This is sometimes referred to as bright finish, which is marketing speak for cheap. And this has no coating on it at all. This is just raw high-speed steel, and frankly not very good high-speed steel at that. This is a low-budget end mill that you'll find on Amazon. And yeah, this guy is going to wear out and get dull much, much quicker than these guys. Now let's talk about flute count. Again, the most common choices you're going to encounter are 2 and 4 flute, and this is certainly sufficient options for the home hobbyist machine shop. There's no hard and fast rules about when to use 2 or 4 flute mills, but there are some general guidelines that you can go by. Each has strengths in different situations. The 2 flute mill gives you much more clearance between the flutes, and this is great for materials that tend to make stringy chips, or materials that are gummy or soft and need more time to get out of the way before that next flute comes around during the cut. And because of that extra chip clearance, the 2 flute mill is much less likely to clog up with material. So this makes 2 flute mills a great choice for things like aluminum, brass, copper, and so on. 2 flute mills are also a good choice when you need to do plunging into material straight down. This is not something that I like to do, but if you need to, 2 flutes are a better choice for that. Now you can get so-called center cutting mills in both flavors, 2, 4, and other flute counts, but regardless of that, the 2 flute is always still going to be a better choice. Now the 4 flute mill, on the other hand, has its own advantages. The first is that because there are more cutting teeth engaged with the material at any given time, it's going to move material faster. But one thing to be aware of is you don't ever want more than 2 teeth engaged with your material at a time, so be thinking about that as your flute count goes up on your mills. The other thing these extra flutes do is add rigidity, so a 4 flute mill is a great choice for tougher materials like steel. You're going to be able to take deeper cuts because the mill itself will be more rigid thanks to these extra flutes. And for materials where your RPM is lower, more flutes is helpful because it allows you to get the same amount of work done with lower RPM because you've got more teeth doing cutting on each lap around. We'll start with this 2 flute mill because it's the easiest to understand, but the basic features are the same on all end mills. So you've got your spiral flutes here on the outside, and similar to a drill, they do serve to evacuate chips, but unlike a drill, they actually evacuate chips outward, not upward, and very much unlike a drill, they are also cutting edges. Now on the end here is where things get really interesting. So you've got 2 more cutting edges here. You can see on this particular mill, the cutting edges along the bottom meet at a point in the center, and that's because this is a center cutting end mill. We'll talk about that a little bit later. But at the business end here, these points here on the end are where all the action happens. And you can see there's these little scallops cut out of the end, and then you can see there's an angle here, and an angle here, and an angle here. These are all relief angles. To understand the end mill, it helps to look at a basic lathe turning tool. So this is a single point tool. This point right here is doing the cutting. And then there's angles here and here and here, and the tool itself sits at an angle like this. So there's all these angles, and these are all relief, clearance, and rake angles. And they all serve basically the same purpose, which is to make sure that this point right here is touching the work and nothing else is. And then there's also, of course, the rake angle, which helps to do the actual cutting. But primarily, it's just all about making sure that only the part of the tool that you want doing the work is touching the work. So you can think of the corners of the end mill as little tiny single point lathe tools. This point right here is what's doing most of the heavy lifting. And then this little scoop cut out here right behind the point, this is the rake angle. And so this is what's creating the right angle at that point for the cutting action for the material. So, if you recall from grinding lathe tools, you want, like I say, a 10-degree top rake on your lathe tool for steel. That's what this little scoop right here is doing. Same thing. Now here on the end, we've got a clearance angle behind this point right here. And then frequently you'll find a second surface behind that at a different angle. So there will be a primary and a secondary clearance angle. And that's because clearance angles are always a trade-off between support and clearance. You want the clearance angles behind any cutting edge to be as shallow as possible because that gives the cutting edge more support. You want support, you want material behind that cutting edge, but the less the angle is, the less clearance you have. You want as much clearance as you can. So there's always a tension there between those two goals. So one of the ways that we get around that is by having multiple clearance angles. So high performance mills, really, expensive mills might even have, 3 different surfaces behind every cutting edge to give as much of a sweet spot between support and clearance as possible. For comparison, here's a more expensive 4 flute mill, and you can see this is not a center cutting end mill. The flutes don't meet at a web in the center, but you can clearly see we've got multiple clearance angles here behind the edges, and There's our rake angle there, again, behind the cutting point, very clearly visible. And if you look closely here on the side flutes, you can again see your cutting edge and a clearance angle there. So anything that cuts has clearance angles. Oh, but that's not all. You remember the lathe tool had clearances in all 3 dimensions on that, around that point. Well, again, every single cutting surface and cutting point on an end mill has clearance angles around it in all 3 dimensions. So another area that shows up here is on the bottom. You might think that these 2 bottom cutting edges are flat because end mills make flat surfaces, but in fact, there is an angle here. They dish into the center. In fact, this is called the dish angle. And it's a little hard to see, but maybe this will help. You see that? This block that I'm holding is machined flat. You can see that the bottom cutting edges there don't touch it all the way across. Only the corners of the mill are touching that surface. That's the dish angle. And this works very much in the same way that a lathe can cut a perfect cylinder because it's a single point cutting tool. The points of this end mill are doing the cutting. And so as this guy spins, it's creating kind of a halo of single point cutting tools effectively. And so as this guy moves across the work, it's like a whole bunch of little single point cutting tools spinning, and they are creating a flat surface. And then these inner areas here are just trying to stay out of the way. If these guys, if you tried to make them flat, they'd end up gouging and touching the surface, and the surface wouldn't end up flat. So this little dish angle here is a subtle little bit of magic. Now we've really just scratched the surface here on end mill geometry. You know, there are land angles and helix angles and chip breakers and gash angles, and there's so much more that goes into end mills, especially high performance ones. But here's a little taste of some of the other geometry that you might see, especially in the home shop, and that's a roughing end mill. The roughing end mill has the side flutes broken up like so. And all that does is lower the tool pressure of the whole cutting edge as a whole, and this allows you to take much deeper depths of cut and move more material in a hurry. Okay, let's do some actual face milling using all the tools that I described earlier. So this is your basic 1/2-inch end mill. And I'm feeding the material right to left because that back edge of that end mill is technically going to be conventional milling if I do it this way. And for feeds and speeds, I will refer you to the Speeds and Feeds video in my Lathe Skills series because I covered milling in there as well. And so at the end of this pass, I use the rapids to come back so that I can again feed in the same direction for the next pass so that that far edge is technically conventional milling. Now, the truth is that this isn't actually that important if you're not taking a very deep cut because, you know, you're only talking, this is a 20 thou pass here, so if you've only got 20 thou of that far flute engaged there, it's fine if you want to mill back the other way. So if you've ever wondered, though, technically why you're not supposed to mill back and forth, this is why. And here's the end result of this style of milling. So you can see the tool marks there and you can tell it was done in multiple passes, but if your mill is set up right, then it'll still feel smooth to the touch. And if I run the needle over that, there's a little bit of a catch, like there's a few tenths there between 2 of the passes, but otherwise it's all smooth. But you will get better results if you can use a milling cutter that's larger than the face that you're milling. So here we are with the 2-inch shell mill, or if you have one of those big carbide insert face mills, those are a great option. And with these guys, it doesn't matter at all which direction you mill in because there's no cutting happening on the front or the back of the cutter. And you're always going to get a nicer result here because while you can still see tool marks, they're very uniform and it's a very nice smooth surface. And lastly, here's the fly cutter. And a fly cutter is a great way to sort of cheat. It acts as a virtual face mill that's much larger than your mill would normally have the rigidity or the power to support because it is a single point cutter, but it is not fast, so you won't be in a hurry with this guy, but it does make absolutely the best finish. And you'll also find out how good the tram is on your head because the larger the cutting radius of your cutter is, the more of a dished effect you'll get if your tram isn't perfect. And the second most common type of milling is side milling, and I would teach you that right now, but I already taught you that when you weren't looking. So here's that footage again. The only thing you need to be aware of here is that there is a lot more cutting edge engaged with the material, so it's asking more rigidity of the cutter, and so you may want to dial down your depth of cut and your RPM a little bit. Now, I promised at the top of the show that I'd talk to you about the dark horse of milling operations, plunging, and I lied. I'm not going to talk about it. I'm going to show it to you. And I lied again, I'm going to talk about it too. So these are both center cutting end mills, which in principle can be used for plunging. I still think it's not the greatest idea to do that with end mills, and you should avoid it when possible. But an example of some places where you might need to do it are if you're trying to get a flat bottomed hole, or if you're doing slot cutting is another common application. And if you need to plunge directly into material, you really want to use a 2-flute end mill if at all possible. And these guys are going to have a pretty good center cutting action, similar to a drill. Now there are also center cutting mills of other types. For example, this is a 4-flute center cutting mill, but you can see what's happening here. It's kind of a compromise. They've got 2 of the flutes meeting in the center, and then the other 2 flutes are just kind of trying to stay out of the way. And so while you can plunge with these guys, it's going to work okay. These outer flutes here are not going to be having a great day, and the edges in here aren't super robust because they're trying to meet in a web while staying out of the way of the other 2 flutes, and it's a compromise. But it turns out to be pretty rare that you actually need to plunge directly into material. Instead, what you can do almost every time is drill out the bulk of the material with a drill, and of course that will leave you with a 118-degree cone in the bottom of your hole as per a normal drill. And then you can come back in here with this end mill and finish it out to final dimension, and then flatten out the bottom of the hole. And that way the end mill isn't doing very much work, it's just the outer edges of the flutes that are cutting. And then if you drill to, say, 20 thou short of your final depth, then you're only having to plunge a little bit with the center cutting action. But the real truth of the matter is that it's very rare that you actually need a flat-bottomed hole. It's almost always easier to just leave a little extra thickness in the material in your design and drill a hole with a drill, and just accept the fact that the bottom of the hole that nobody will ever see has a little bit of a cone in it, and you can still accommodate your alignment pin or whatever else is going in that hole. But in machining, the devil is always in the details. If you genuinely do need a flat-bottomed hole, then this trick with a center cutting end mill won't actually even work, because remember, there's a dish angle on the end of this. And it's slight, it's only a few degrees, but technically, if you plunge down into your material, you're going to end up with a little bit of a cone in the bottom. So if you do genuinely need a precisely flat-bottomed hole, your best bets are going to be the boring bar on the lathe or a boring head in the mill. And remember, you can learn a lot about whether your milling technique and your speeds and feeds are right by looking at your chips. So for regular face milling type operations, you want to see these kind of comma-shaped chips like this guy here. And when side milling, you're looking for these icicles like this guy here. The big thing to watch out for is powdery, dusty looking chips. If you see that, it means your tool is doing more rubbing than it is cutting, and that's really bad for the tool. So figure out what's going on with your feeds and speeds. Your tool pressure might be too low, the tool might be dull, something like that. So look out for those commas and those icicles. And when you're done, store these with your fingernail clippings, as is tradition. What? Does nobody else do that?